Section 3.2, implicit differentiation. Implicitly defined functions. The graph of the equation, that one, has a well-defined slope at nearly every point because it is the union of the graphs of three functions, which are differentiable except at O and A. But how do we find the slope when we cannot conveniently solve the equation to find the functions? So in other words, they're saying, how do we get y by itself there? That would be very inconvenient. So we have to find another way to find the derivative. The answer is to treat y as a differentiable function of x. Y is equal to something, we just don't know what that is. And differentiate both sides of the equation with respect to x. Using the differentiation rules, sums, products, and quotients, and chain rules. So we're going to use all the rules of differentiation, but we're going to pretend that we know what y equals. And so there's really this inside function for y equals something. And every time we take the derivative of y, we're going to multiply times the derivative of the inside. For example, and I'm not going to do this whole derivative, but the derivative of x to the third is 3x squared. And as long as we're doing the derivative of x, we're just going to do normal derivative. But then the derivative of y to the third is 3y squared, but we know that y is equal to something. We just don't know what it is. So we're going to represent the derivative of that by just multiplying by dy dx. In other words, times the derivative of the inside. And then we'd minus 9 times first times derivative of the second on this one, which is 1, but then times dy dx. So every time we take the derivative of y, we're going to include that chain rule, the derivative of the inside. And then plus second times derivative of the first is equal to 0. Let's keep going. Let's not finish this one right now. Let's see, the process by which we find dy dx is called implicit differentiation. So this is implicit. Differentiating implicitly. Find the derivative of y with respect to x if y squared is equal to x. Now we can solve for y here. It's plus or minus square root of x. Now I'd be okay if we were finding the derivative of just square root of x or just negative square root of x, but I don't want to really take the derivative of plus or minus square root of x. So we can do this implicitly. The derivative of y squared is 2y dy dx is equal to 1. So the derivative is equal to 1 over 2y. Now instead of basing the derivative off of the variable x, we just base it off of y. Example 2, finding slope on a circle. Find the slope of the circle x squared plus y squared equals 25 at the point 3, negative 4. So the derivative of x squared is 2x. The derivative of y squared is 2y. But then we'll multiply times dy dx is equal to 0. Now keep in mind we're taking the derivative of everything. So the derivative of 25 is 0. Now let's get dy dx by itself. And then we'll divide by 2y. And that's negative x over y. Now we're asked what the slope of the circle is at that point. Now we're going to evaluate at the point 3, negative 4. So x is 3, so negative 3 over y is negative 4. The slope is 3/4. So the slope of that line right there is 3/4. Solving for dy dx, show that the slope dy dx is defined at every point on the graph of 2y equals x squared plus sine y. So the derivative of 2y is 2 dy dx. Derivative of x squared is 2x. And then we have cosine of y dy dx. All right, let's get the dy dx's together on the same side of the equation. We have minus cosine of y dy dx. That's equal to 2x. Let's factor out the dy dx. And that leaves us 2 minus cosine y dy dx is equal to 2x over 2 minus cosine y. Now the biggest y can be, or the biggest cosine of y can be, is 1. So 2 minus cosine of y is always greater than 0. It can never be 0. So that's why the slope is defined everywhere, because we can't, the denominator has no chance of being 0. Tangent and normal to an ellipse. Find the tangent and normal to the ellipse at the point -1, 2. See figure 3.1.1. So the point is -1, 2. So we already have the point. We need the slope. Well, the derivative of x squared is 2x, and then we have, that's actually a minus. Minus first times derivative of the second. And the derivative of y is 1, so that's just going to be 1 times then the derivative of the inside, plus the second times the derivative of the first, and the derivative of x is 1, plus 2y dy dx is equal to 0. Let's get the dy dx's together. That'd be -x dy dx plus 2y dy dx is equal to, let's minus the 2x over, and we'll have this negative y, so we'll have to add the y over. So y minus 2x. We can factor out a dy dx, and that's -x plus 2y equals y minus 2x. Now that's multiplication, so now we can just divide, and we have dy dx. So dy dx is now equal to y minus 2x over, and then we could make this, we can make that 2y minus x. 2y minus x, and we're evaluating this at the point -1, 2. So y is 2, x is -1, y is 2, x is -1. So 2 plus 2 is 4 over 4 plus 1, 4/5. Y minus 2 equals 4/5 times x plus 1. That's the tangent and the normal. Y minus 2 equals -5/4 times x plus 1. Derivatives of higher order. Implicit differentiation can also be used to find derivatives of higher order. Here's an example. Find a second derivative implicitly. Let's do the first derivative. Derivative of 2x to the third is 6x squared. And then we have minus 6y dy dx is equal to 0. So -6y dy dx is equal to -6x squared. Dy dx is equal to, it's just going to be x squared over y, because the -6's will cancel. So there's the first derivative. Now let's do the second derivative. d2y over dx2 is equal to bottom times derivative of the top minus the top times the derivative of the bottom. The derivative of the bottom, the derivative of y is 1, but then we're doing this implicitly, so times dy dx. And that's all over y squared. So we have 2xy minus, we know what dy dx is. This is dy dx right there. So minus x squared times x squared over y squared. That's equal to, now we need to get rid of the complex fraction, so I'm going to multiply everything times y. 2x y squared minus x to the fourth over y squared. Using the rational power, we've already kind of talked about this, where this is x to the 1/2. That's 1/2 x to the -1/2, 1 over 2 square root of x. This is 2/3 x to the -1/3, so it's 2 over 3x to the 1/3. And even with this, it's -1/5 cosine of x to the negative, I need it to the negative. I'll just start over. -1/5 cosine to the x to the negative 6/5, and then times negative sine of x. So we have negative times the negative is a positive. We have sine of x over 5 times the 5th root of cosine to the 6th x. 3 multiple choice challenges. Here are 3 multiple choice questions that most calculus students get wrong because they fail to handle the chain rule properly. See if you can answer them before looking at the solutions. In any case, be sure to study them carefully so you can avoid making similar mistakes. All right, now I got to be careful. If dy dx equals 1 plus sine of y, then the second derivative is equal to, okay, cosine of y times dy dx, but we know what dy dx is. That's cosine of y times 1 plus sine of y. So if you distribute, I think we're getting letter D as the answer. If x equals sine of t and y equals cosine of t, then the second derivative would be, all right, I gotta be careful here because they say it's easy, it's easy to make these mistakes, I guess. Cosine of t, so dy is negative sine of t over, so dy over dx is cosine of t. Now that's equal to negative tangent of t. Now, so the second derivative is negative secant squared t. Negative secant squared t. Letter B. On number 3, if y equals f of t squared, the inside function is t squared. So that means if the derivative of f is this with just x, then we've really multiplied by 1. So if we're doing the derivative of this with t squared on the inside, then it's going to be 2t square root of 2 minus cosine of t squared, because then we would take the derivative of the inside, which would be 2t. So the answer here is letter B. In exercises 1 through 8, find dy dx. Let's try, how about number 8? Seems interesting. 1 plus cosine of y dy dx is equal to first times the derivative of the second plus the second times the derivative of the first. Here we have cosine of y dy dx minus x dy dx equals y minus 1. Now we're going to factor out a dy dx, and that's cosine of y minus x is equal to y minus 1. And now we just divide. So dy dx is equal to y minus 1 over cosine of y minus x. Find dy dx and find the slope of the curve at the indicated point. Let's do number 12. So we have 2 times x plus 2 times y plus 3, but then times dy dx is equal to 0. dy dx is equal to, we're going to minus this over and divide by that one. We get negative 2x plus 2 over 2y plus 3. So negative x plus 2 over y plus 3. And we're evaluating this at 1, negative 7. So negative 1 plus 2 over negative 7 plus 3. So negative 3 over negative 4, 3/4. Find where the slope of the curve is defined. Oh, let's do 14. So 1 is equal to negative sine of y, and then dy dx. So dy dx is equal to negative 1 over sine of y. So we say defined everywhere except when sine of y is equal to 0. Find the lines that are tangent and normal to the curve at the given point. How about number 20? We get 2y dy dx minus 2 minus 4 dy dx is equal to 0. So we're going to factor out a dy dx, and that's going to give us dy dx times 2y minus 4 is equal to 2, and then divide. So dy dx is equal to 1 over y minus 2, because you can factor 2 out of that, cancel with the top one. We're going to evaluate that at the point negative 2, 1. But we're only using the y value. We have 1 over 1 minus 2, negative 1. So the tangent is y minus 1 is equal to negative 1 times x plus 2, and the normal is y minus 1 is equal to 1 times x plus 2.